We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will conclude our study of fluids by extending our study to systems in which the fluid is flowing. We will limit our discussion to ideal fluids, namely the smooth flow of incompressible, zero-viscosity fluids. We will then move on to consider flow in pipes whose area and height can change to derive Bernoulli's equation that relates the pressure change in such flow to the change in the kinetic and gravitational potential energy densities of the fluid. To this point, our discussion of liquids and gases has been limited to systems in static equilibrium, allowing us to understand how pressure changes with depth and to quantify the buoyant force on objects which are partially or totally submerged. In this pre-lecture, we will use Newton's laws to extend our treatment to systems in which the liquid or the gas is flowing. Understanding the flow of fluids is, in general, a very complicated problem unless some simplifying assumptions are made. While these assumptions will limit the range of actual situations to which we can apply our equations, the development and the form of these equations will still give us great insight into the behavior of liquids in general. In what follows, we will assume that we are dealing with ideal fluids. An ideal fluid is a liquid or a gas with the following properties. 1, it is incompressible. By incompressible, we mean that the density of the fluid cannot change. This assumption is very good for many liquids, like water, for example, but it can even be a reasonable approximation for gases in certain situations. 2, it has zero viscosity. That is, it flows without friction. 3, it flows smoothly and without turbulence. One of the defining assumptions for an ideal fluid is that it is incompressible. This property alone will yield a very important relationship describing the properties of moving fluids, called the continuity equation. If a fluid is incompressible, then a certain mass of the liquid always occupies the same volume, no matter the shape of its container. Here we see water flowing through a pipe consisting of 2 cylinders having different cross-sectional areas joined by a transition piece. Since water is incompressible, the amount of water flowing past any part of the pipe during a specific time interval must be the same. This result is a simple consequence of the fact that whatever goes into one end must come out the other. The amount of water that flows past a point in the pipe in a time dt is just equal to the volume of the column of water that passes in this time, which is equal to the product of its area and its length. Since the fluid is incompressible, the density of the fluid must be the same everywhere in the pipe. Since the length of the volume is equal to the product of the speed of the flow and the time interval, we obtain the important result that the product of the area of the pipe and the speed of the flow must be the same for all parts of the pipe. This equation is called the continuity equation. Thus we see that as the diameter of a pipe decreases, the speed of the flow through it must increase. You are probably already familiar with this result if you have ever put a small nozzle at the end of a garden hose in order to increase the speed of the water leaving the hose. We will now do a simple example to illustrate the usefulness of the continuity equation. Here we see a pipe in the basement of your house that carries water in from the city supply. As you open up a faucet to your bathtub, you see the water flowing out of the pipe at 4 meters per second. If the diameter of the upstairs pipe is half that of the basement pipe, what is the speed of the water in the basement pipe? In order to answer this question, we simply apply the continuity equation. Namely, The product of the area of the basement pipe and the speed of the flow there must be equal to the product of the area of the faucet and the speed of the flow at the bathtub. Since the area of the pipe is proportional to the square of its diameter, we see that the speed of the flow in the basement must be 1/4 of the speed of the flow at the bathtub, or 1 meter per second. We have just shown that the speed of the fluid in a pipe needs to change whenever the diameter of the pipe changes in order to keep the flow rate the same. If the speed of the water is changing, then so is its kinetic energy. If its kinetic energy is changing, then there must be forces acting that do work on the water. What are these forces? How can we quantify them? We will start by looking at the flow in a pipe whose cross-sectional area is reduced along the flow as shown. We will color a volume of the water red and follow its flow in time. During the time it takes this volume of water to flow past point 1, the same volume of water will flow past point 2. The change in kinetic energy of the red water during this time will be the kinetic energy of the water that flows past point 2 minus the kinetic energy of the water that flows past point 1. The work done on the red water by the pressure in the left part of the pipe is equal to the product of the force exerted by this pressure and the distance the water moves. In the same way, the work done on the red water by the pressure in the right part of the pipe is equal to the product of the force exerted by this pressure and the distance the water moves. Note that the work done by the pressure on the right is negative, since the force due to this pressure points in the opposite direction of the flow of the water. We will now use the work kinetic energy theorem to equate the forms for the change in kinetic energy and the work done by the pressure to obtain an important relationship. This equation can be simplified by noting that both the masses and the volumes involved at point 1 and point 2 are equal. Note that our final result implies that at points in the flow where the pressure is larger, the velocity must be smaller. We can understand this dependence in terms of the forces that are acting. Namely, as the fluid moves from a region of high pressure to one of low pressure, it speeds up, since the direction of the net force is in the same direction as the movement of the liquid, causing it to accelerate. So far, we have considered flow along a horizontal pipe where the only work done on the fluid was due to differences in pressure. We can easily generalize this result to the case where the fluid flows in a pipe whose vertical height is changing by just including the work done on the fluid by gravity. In this case, the change in kinetic energy of the flowing liquid is equal to the sum of the work done by both pressure and gravity. The derivation is very similar and results in the addition of a term on either side of the equation that represents the gravitational potential energy per unit volume of the fluid. This equation is often referred to as Bernoulli's equation. Note that in the static limit, that is, V1 equals V2 equals 0, we recover our result from last time that relates the pressure to the depth. Before we close this unit on fluids, we want to point out the similarity of this result to the one we obtained way back in Prelecture 8. Namely, if we ignore the pressure terms, we obtain an equation that looks just like the one we used to describe the energy of an object upon which only gravity is doing work. For example, a drop ball or a train on a frictionless roller coaster track. The only difference is that the mass m has been replaced by the mass density rho. Therefore, for a liquid, we interpret these terms as the kinetic and potential energies of the liquid per unit volume. So what about the pressure term? Does it refer to some kind of energy also? Well, last time we saw that the pressure in a liquid is due to the random motions and collisions of the molecules that make up the liquid. The pressure appears in our energy conservation equation because it represents the internal energy of the fluid per unit volume, the density of energy associated with the random motions of the molecules of the liquid. We will close with a problem that illustrates the use of Bernoulli's equation. Here we see a pipe in the basement of your house that carries water in from the city supply. Up on the first floor, 4 meters above the basement pipe, you open up a faucet to your bathtub and see the water flowing out of the pipe at 4 meters per second. The diameter of the upstairs pipe is half that of the basement pipe. What is the difference in water pressure between the basement and the upstairs? We start by writing down Bernoulli's equation. We can solve this equation directly for the pressure difference between the input and the bathtub. The only term we can't immediately evaluate on the right-hand side of the equation involves the velocity of the incoming water. We can evaluate this term if we use the continuity equation that relates the ratio of the velocities to the ratio of the square of the diameters of the pipes. Indeed, we found this velocity to be equal to 1 meter per second in the example a few slides ago. If we now plug in the remaining numbers, we find that the pressure in the basement pipe must be bigger than the pressure upstairs by 46,700 newtons per meter squared, or 46,700 pascals, the SI unit for pressure. We conclude with a brief discussion of the main points of this pre-lecture. First, we derived the continuity equation for an ideal fluid, that is, a fluid whose density does not change and flows without friction or turbulence. In particular, by considering flow through a pipe whose cross-sectional area changes, we determined that the product of the speed of the flow and the cross-sectional area of the pipe through which it flows is a constant. Second, we used the work kinetic energy theorem to determine that the sum of the work done by the pressure in the fluid and the kinetic energy density of an ideal fluid is a constant at any point in the flow. By considering ideal fluids that flow from one height to another, we derived Bernoulli's equation, that the change in pressure of an ideal fluid between 2 points is equal to the sum of the changes in the kinetic energy density and the gravitational potential energy density of the fluid.